The AK-47 is widely regarded as an indestructible machine, a weapon capable of being buried in mud, left for decades, and still firing without fail. For decades, a persistent explanation for this reliability has circulated among firearms enthusiasts: the idea of loose tolerances. The theory suggests that the rifle functions in harsh conditions, specifically because it was manufactured with sloppy internal clearances, giving dirt and debris room to move without jamming the action. This 1978 East German repair manual provides the empirical data to test that theory. It serves as a strict diagnostic roadmap. Treating this document as a forensic guide, we will map the mechanical boundaries and observe how the system fails. What emerges is proof that a functioning AK-47 requires exact physical relationships. Pushing the internal components past rigid engineering limits results in predictable systemic malfunction. The mechanical cycle begins with thermodynamics. When the primer ignites the M43 cartridge, the propellant burns, generating a rapidly expanding volume of high-pressure gas that pushes the bullet down the barrel. Near the muzzle, a small aperture called the gas port captures a fraction of these expanding gases and channels them upward into a cylindrical housing known as the gas tube. Striking the face of the gas piston, this sudden thermodynamic pressure translates directly into mechanical energy, violently driving the attached bolt carrier rearward. This text from Section 3 of the NVA manual documents the exact threshold where this gas system fails. Armorers are instructed to measure the radial play between the gas piston and the gas chamber walls. If the gap between them is greater than 0.2 millimeters, the piston must be replaced. A gap exceeding 0.2 of a millimeter creates excessive volumetric space. The high-pressure gas simply blows past the piston head, bleeding off the kinetic energy required to push the heavy bolt carrier assembly all the way to the rear. The cycle halts entirely. The powerful, continuous cycling of this gas-operated rifle system relies absolutely on tight, strictly maintained volume-to-pressure dependencies. The system breaks down the moment its internal clearances become too loose. As long as the gas seal holds, the carrier assembly continues its violent linear travel toward the rear of the receiver. Machined into the underside of the bolt carrier is a precise, curved channel called the cam guide. As the carrier moves straight back, this guide acts as a lever against the bolt itself, forcing it to rotate on its central axis. This specific rotation clears two thick steel locking lugs from deep recesses cut into the front trunnion, physically unlocking the breech. Now free from the trunnion, the bolt slides backward alongside the carrier. An extractor claw grips the rim of the spent casing, pulling it from the chamber until it strikes the ejector and is expelled from the rifle. Having bottomed out against the rear of the receiver, the tensioned recoil spring drives the entire assembly forward again. The bolt strips a fresh cartridge from the curved 30-round magazine and feeds it directly into the chamber. In the final fraction of forward movement, the cam guide forces the bolt to rotate in the opposite direction. The locking lugs slide back into their trunnion recesses, sealing the breech. The rifle's ability to safely contain thousands of pounds of chamber pressure depends entirely on the synchronized geometry of these cam paths and locking lugs. To understand how the weapon resets for the next shot, we look at the fire control group, the mechanical timing center responsible for releasing the hammer. When the external safety lever is pushed to the lowest position, the